joining us on this webinar on controlling Ethernet IP. We'll do the usual run of it. Presentations are roughly about 16 minutes, but at any point if you have a question, just feel free to put it in and we'll get to that in the end.
Hello and welcome to today's webinar. Today, we will look at controlling Ethernet IP with a Horner controller. Horner has supported Ethernet IP for a number of years, but only as an I/O adapter. Today, we will look at new functionality coming to Horner controllers, which allows your controller to fully control a network of its own. Let's look at the agenda for today. First, we will start with a review of Ethernet IP in general. Then, we will look at using the new Ethernet IP scanner functionality with a Horner controller, followed by the supported models. There will be demonstrations throughout, and we will finish with a Q&A session. What is Ethernet IP? Ethernet IP is an industrial network protocol that adapts the Common Industrial Protocol, or CIP, to Ethernet. Ethernet IP is one of the leading industrial protocols and is widely used in a range of industries. While most often associated with the American automation control company Rockwell Bradley, Ethernet IP is an open protocol based on a much older protocol named ODVA. Ethernet IP utilizes standard Ethernet components unlike EtherCAT and Profinet IRT. It utilizes both TCP/IP and UDP elements of Ethernet. Ethernet IP is based on an object model. In the diagram on the right, we can see the network device, or CIP node, represented as a series of objects. The gray box represents the CIP with functions by using each object instance inside of it. This object model is how Ethernet IP functions. Now, we are going to look at some of the key objects that are most often used. First, Ethernet IP represents data using assembly objects. Known as superobjects, this object acts as a convenient package for transporting data between devices. The input assembly moves data to the scanner or network controller, and the output assembly moves data away from the scanner or network controller. Ethernet IP also tries to standardize device setup for easier communication. Application objects are used to define data in the device, and they are specific to each device type and function. All CIP devices of the same type must contain the same application-specific objects, which is where we use device profiles. These contain a set of application-specific objects for a particular device type. Many are predefined and are made to assist users when working with devices of the same type from multiple different vendors. Next, let's look at the two different types of messages on Ethernet IP. Explicit messages, or TCP messages, are Ethernet-based messages with built-in error checking. These are best used for point-to-point requests sent on an infrequent or as-needed basis. They follow the request-response model, and each message explicitly states data being requested. For example, imagine we have a variable frequency drive on our network. It could have hundreds of parameters, but occasionally we will need to read or write a specific parameter. In this case, we would likely use an explicit message, as it is an infrequent specific request. However, for runtime, high-speed messages would use implicit messages, or UDP messages. Ideal for continuous real-time data, this message type follows the producer-consumer model. These messages contain only data. The meaning of the data is pre-established. For an example, again, imagine our variable frequency drive. Implicit messages might be used for the start-stop status, predefined frequencies, the current frequency, and so on. With that covered, let's now look at what device classes might be receiving these different messages. The device that controls the network is known as the I/O scanner. You must have at least one of these for your network to function. Next, the most common member of an Ethernet IP network is the I/O adapters. These could be variable frequency drives, I/O blocks, or anything else that interfaces with the network. Next, we have devices that exchange data using explicit messaging. These are our explicit message clients. Usually in a network, these would be your HMIs or other devices with the capability to read and write data to the network. And finally, we have a very simple device known as an explicit message server, which simply responds to explicit message requests when they receive them. With Horner, we have traditionally supported several parts of this network. All Horner all-in-one modular controllers can act as both I/O adapters and explicit message clients. But today, we are showcasing the new I/O scanner functionality. Any Canvas, XL Prime all-in-one, or modular controller can now be used as an I/O scanner on your network, as long as you are using Seascape version 10.2 and your Horner controller is updated to firmware version 17.4. And with this new functionality, it is now possible to run an entire network of third-party devices with a Horner I/O scanner controlling them. Which Horner products support Ethernet IP scanner functionality? To start with, all Canvas series controllers include support as standard. Whether it's a Canvas all-in-one or a modular CPU, both will support this new feature as standard. Ethernet IP scanner functionality is also supported in the XL Prime series of controllers. However, it does not come as standard. Instead, it requires a one-time purchase of an Ethernet IP scanner license. What are the Horner Ethernet IP scanner features? Of course, the Ethernet IP scanner allows you to control your Ethernet IP network, but beyond this, we can also exchange I/O data with I/O adapter devices in real time, including third-party I/O adapters. And when configuring third-party devices, Horner controllers allow you to import device info from an EDS file. Horner controllers also have the ability to create explicit messages for triggered data exchanges. Both of these features will be demonstrated later in this webinar. Let's now look at the workflow for setting up the Ethernet IP scanner functionality in your Horner device. Starting with Seascape 10.2 Service Pack 2, a new option will be available in the LAN configuration menu in Seascape. First, we enable this new option named Enable Ethernet IP Scanner from the list of resident protocols in LAN 1 or LAN 2. Next, we highlight Ethernet IP Scanner and click on the Configure Selected Protocol. And here, we assign an Ethernet IP Disable variable and Ethernet IP Status variable. Next, we are going to add I/O adapters to the network by right-clicking on Ethernet IP Resident Protocol. In this menu, navigate to the Adapter tab and fill in your adapter's details. Then, we simply need to fill in the details for the input, output, and configuration assemblies. If you've imported data from an EDS file, these will all be automatically configured, but we would just need to manually assign a few things. A local variable to transmit data from the device or receive data from it, an RPI or requested packet interval. We have to select whether we're using unicast or multicast. And finally, we have to assign the I/O data to a local variable. Remember, not all I/O adapters support all three types of assemblies. With that covered, we're going to switch to a demonstration of this workflow. Here we are on the bench with the equipment we are going to use for today's demonstration. We have the Horner CPU 300 modular controller, which is connected to a HMI Connect touchscreen. And to demonstrate the Ethernet IP functionality, we have an Encoder Products Ethernet IP compatible encoder, which will interface with our Horner controller as an I/O adapter. Now, let's look at Seascape. First, we navigate to Hardware Configuration at the top. Then, we are going to click on LAN 1, as this is where we are connecting our Ethernet IP network. Starting with Seascape version 10.2 Service Pack 2, you should see an Ethernet IP scanner checkbox under Resident Protocols. Then, we are going to click Configure Selected Protocol. Here, we need to assign a Boolean disable variable and a double integer status variable. We have pre-configured these variables for our demonstration, so we simply select them from the list provided. With that completed, we now need to start adding I/O adapters to our network. First, we navigate to the Ethernet IP scanner checkbox option, but this time we right-click the text instead and click Add Adapter from this dropdown. In this menu, we will start configuring our I/O adapter. We are going to name it encoder and provide the IP address for it. Next, we need to install the assembly details. If the manufacturer provides an EDS file, then we can simply select Browse for EDS file and navigate to the file's location. It will then ask if we want to import the EDS file, to which we select Yes, and then we are given a few different profiles or setup options. Remember, not all manufacturers will provide this many options, but some will. For this demonstration, we are going to select the default option, and then we assign a connection timeout value. We've chosen 500 milliseconds, but this will change depending on your operation. Next, we need to assign a Boolean disable variable and a double integer status variable for the encoder itself. Again, for this demonstration, we have pre-configured these variables, so we will just select them from the drop-down menu provided. With that completed, we have successfully set up our encoder. However, we still need to configure the data coming from the encoder. First, we decide a data type. In this case, since the data is 4 bytes long, the best choice is a double integer. Next, our RPI, or requested packet interval, we are going to change to 50 milliseconds. But this can be whatever you like. Finally, we need a local variable to store the data, which we have already configured under the name EIP encoder position. We are now done with our setup for this encoder, as we have no output or configuration data to deal with. We also don't need to set up explicit messaging, but we will show off this functionality in the next demonstration. For now, let's jump back to the bench and take a look at our encoder at runtime. Here we are on the bench. Our program download has been completed, so this should be all working as we configured it to. If we move our encoder, we can see the position value on our screen update in real time. Down here, we also have some status information. For main Ethernet IP status, the number represents how many adapters our Horner Ethernet IP scanner is communicating with. This value should be 1, as we only have the encoder connected to our network. And as we can see, it is indeed 1. For the encoder EIP status, any value other than 1 would indicate a problem somewhere in the system, but as you can see, our current value is 1. In our second and final demonstration today, we are going to look at how to configure explicit messaging in Cscape. This will be a very simple example where we are going to configure one specific message to retrieve a parameter from our device. In this case, our encoder. Now, let's jump back to Cscape and set this up. Here we have the screen from our previous demonstration, but we have made some changes. We still have the main EIP status and encoder EIP status boxes, but we have added a third box for our encoder reported state, which will be populated with data we retrieve using an explicit message. We are going to navigate to hardware configuration at the top, click on LAN 1, double click on encoder under the Ethernet IP scanner checkbox, and then into the explicit message tab at the top. First, we click enable explicit messaging. Then, since we are only retrieving a single value, we are going to choose get attribute single from our dropdown. Next, we need to fill in our class, instant, and attribute fields. To get this information, we referred to the documentation. As you can see, we are going to be looking for class 1, attribute 8, but there is no mention of an instance. This is because for most devices, only one instance is used. So, filling this information into Cscape, our class will be 1, our instance will be 1, and our attribute will be 8. We leave source type as integer and length as 0. We also leave source data blank, as in this example, we are only retrieving a single attribute. Then we need to configure a trigger and status variable as before. But then we also need a response data variable to store any data that comes back to the device. This is a 256-bit array, so it can support quite long messages. However, in this demonstration, our response will only be 4 bytes long, and we use the response length variable to tell our machine how long our message is supposed to be. And that's everything configured. Now, let's jump to the bench and see if it works at runtime. Here, we can see the box where the message should appear. Currently, it says none, as we haven't executed an explicit message yet. If we press this Get button, we can see it change to ready. That is a simple example of an explicit message transaction between our Horner controller, acting as an I/O scanner, and our I/O adapter. And that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so as usual, the upcoming webinars are up on the webinar section of our website, as well as in the newsletters that you will have been sent. The registration links are there now, so feel free to join for the upcoming. I don't see any questions in on today's webinar, so I think we can leave it there. Thank you all very much, and we'll see you next time.